Thank you very much. Thanks to the organizers for putting this together and giving us the opportunity. If you are interested in the tensor group, we do have homework you were supposed to have done beforehand, but we'll let you do that, but you're going to have a busy evening tonight. So, right. So let's let A, B, and C be some finite dimensional vector spaces. Like A will be of dimension A, B will be of dimension B, C will be of dimension C. Maybe I'll change the field later. And what is a tensor? Well, we could think of it as a trilinear map. That's tensor T, that each three vectors and spits out a number. Just like with matrices, you could think of a matrix as something that eats a vector and gives you another one, or it can eat two vectors and gives you a number. This could also be as a map, say, well, T, let's say from A star, tensor B star. Well, let me write it differently. Let's say A star to B tensor C, etc. This point of view is particularly interesting because this is a space of matrices. And so you can think of a tensor as a family of matrices. And there's been a lot of ongoing work to study invariance of tensors. And specifically, I want to sort of group them into two types, cost and value. So cost is rather easy to describe intuitively. We could think of this as a trilinear map. It eats three vectors, spits out a number. How much work do I need to do to compute that? For example, if I have in the matrix world, if I have a rank 1 matrix, I can factor it as a column vector times a row vector. And if I want to do matrix multiplication with a rank 1 matrix, it's very cheap, much cheaper than a random matrix. And so the cost of a trilinear map, but so this week, I'm told you're supposed to, this is for graduate students and postdocs, to get involved in some research project. And it would be criminal for me to ask you to study cost of tensors because the algebraic geometers have been on that for over 100 years. But what's brand new, to me at least, is value. So there's 100 years of study here, and value, up until very, very recently, this was considered, as I'll explain momentarily, something related to probability or combinatorics. And the goal is, well, first go to algebraic geometry. And once we're there, you'll see it'll lead to commutative algebra. And the point about this project specifically, tomorrow Claudia is going to tell you about a different project involving tensors, is that this has not been done. So it's a very ripe area for new investigation. So let me be a little bit more precise. But first, I should give you an example of a tensor. Let me give you an example of a so let's say A is an algebra, finite dimensional. And given an algebra, we get its structure tensor. So this is a map, I guess, from A cross A to A. It eats an element of the algebra A, eats the second element of the algebra B, and spits out their product. So this structure tensor lives inside the dual of A, tensor the dual of A, tensor A, based on the conventions of the previous board. Any questions? No? So there's one algebra we learned about before we knew what an algebra was. A is just the space of n by n matrices. And so here there is a famous question. What is the cost of this structure tensor? So this eats a matrix, eats a second matrix, spits out a third matrix, n by n. And the naive algorithm, well, if I'm multiplying two matrices, well, to get this entry, I have to do, say, n multiplications, n minus 1 additions. So it costs on the order of n cubed arithmetic operations. And then there's a theorem, Strawson, that you can do better. Actually, if you know about secant varieties and computing their dimension, you would not have needed Strawson to know that. But that's not today's talk because that's been well researched. But I can say that there's this astounding conjecture that as n goes to infinity, the cost is nearly as cheap as it is to add matrices. So to add matrices, of course, you just have to do n squared additions. But I don't want to talk about that today. But every mathematician should know about it. So you can ask me about it afterwards. I'd be delighted to spend the next 3 days telling you about it. So I want to go back to this, start introducing this notion of value. And I'll introduce it actually via combinatorics. So now let F be finite field. Let's say Fp, for example, some prime number p. And you're handed T. So conjecture / theorem now due to many people, but most recently Cohen and Moshkovitz. The conjectures many people, including Gowers and others. If the trilinear map T is biased, I'll explain that what that means, then T has structure. So it's easy to see the other way around. If you have a tensor with some special structure, viewed as a function, it will not behave like a random function. And this is the converse of that. So let me be more precise. So
the structure is not just simply bias.
Thank you. So I noticed the people in the first two rows have been very freely commenting. I would be delighted if the people in the last 5 or 6 rows would share their thoughts, complaints, questions, because this is not for these people. These people, they know me. I know them. No questions? Okay. Sorry? Yeah, I'm gonna define it for you very soon. But first, let me define bias, because at least for me, that's not obvious. So explicitly, well, let's say f is any function from any set to some finite field. Then we could define the bias of f to be, well, the expectation over, you average over all the points in your source. And then, well, it's difficult to detect a bias here, so let's work on the unit circle. And if you think about it, this is the average value of the function. And if the function is taking values on the circle and it's random, we would expect the average value to be 0. Good, good, good. And it wasn't even some only people in the first row. Right. And so in our case, Z is just going to be this product of these 3 vector spaces. And Ft is trilinear. The easiest possible case. Now, you may say, okay, well, you're doing that because you like to do algebraic geometry and tensors. This was not me. This is like Gowers. I mean, serious analysts studying this problem. Anyway, he's not afraid of scary things.
These are over the same finite field.
So everything is over FP for now. And yeah, so if, let me say it, if T is random, the bias of T is 0. So, okay. So now there's all these other notions of tensor rank. And so it's useful to sort of slightly change the way we do our bookkeeping. And instead, define analytic rank of T to be minus log over F of the bias of T. So if T is in FPM cross FPM cross FPM, then this will be and random, and I think P large maybe. I'm not sure about that. This will be around M, which if you think about matrix rank, the maximum value of a matrix rank is M, and these measures of value will be more like matrix rank than other measures of tensor rank, because the maximum possible value of them will indeed be the, as a physicist would say, local dimension, this M. Okay. So analytic rank. And now I want to talk about the measure of structure. So this will be called slice rank. But this will take a few steps. So first, no matter what tensor measure you have, you generally say that T has rank 1 if it's like a matrix of rank 1. If it's a row vector, a column vector times a row vector times a vector sticking out of the blackboard.
Random tensor is phi of 0. How do you take its log?
Let's not worry about that right now. They have a convention for log of 0, and I will not remember it right now. But we're gonna leave the world of finite fields momentarily. But first, I need to tell you where everything is coming from. Right. So T has rank 1 if it's like that. Some A in A, a column vector, a row vector, and a vector out the blackboard. And well, the tensor rank is usually defined to be the smallest r. Let me define slice rank now. I can do that first. So this slice rank of T it's a little complicated. It's the smallest row such that there exists row 1, row 2, row 3 summing to row, that T is equal to some j equals 1 to row 1 of aj tensor xj plus some summation k equals 1 to row 2 bj tensor yj bk tensor yk, and maybe I need to do a permutation here so that we have A, B, and C orders plus some summation w equals 1 to row 3 zj tensor cj. And this was introduced by Terry Tao for studying problems in combinatorics, and was very useful for giving insight to those problems. Yeah, so then ignore this middle one, right? Here we have a vector tensor matrix, and here we have matrix tensor vector, and here I lack good notation for writing, yeah, the vectors in the middle. So I just, sorry. Other questions? Further back? Yeah. No, just sigma 1, 2, I permute the first and second factors just so the vectors in the middle, and I want the matrix to be like in the first and third slot. I don't know good notation for it. Sorry. Other questions? Okay. So, right, but I'd be remiss if I didn't tell you cost. So the tensor rank, just for comparison, is the smallest r. Oh, so this is any field. So for us, there's only 2 fields. Well, one in a series. Smallest r such that well, let me introduce some notation. Let me let M1 direct some R. Let me call, well, it's too high up. M1 direct some R to be sitting inside CR tensor CR tensor CR, or FR, whatever F is. So this is the sum of R disjoint rank 1 tensors. And the cost, yeah, smallest r such that T is a sum of R rank 1 tensors, not necessarily disjoint, but this is bad from the point of view of algebraic geometry because it's not, question? I wish I knew. It's easy to define, not so easy to compute. Well, easier to define than compute. Easier said than done, or whatever. Yeah, and in fact, if you are in the tensor group, that will be one of our problems. Yeah, so so there's very few examples. So I don't like to sort of, I hate to do this, but I tell you, so somebody asked me to compute the, well, let me do algebraic geometry. R of T, smallest r such that T is a limit of so the way I got involved in this business is I was having dinner with a mathematician who I did not know before that dinner, really. And he told me there was an open problem about computing this thing, which is the border rank of a very explicit tensor in C4, tensor C4, tensor C4. And I made the mistake of laughing at him. At which point, he offered me a bottle of champagne if I could solve the problem for him. I thought it was a homework problem, but I thought I'd be cautious. This was like in September. I said, I get it for you by Christmas. 4 years later, it got solved, but it's not so easy. So and that's just for a very small particular one, which you would think would be easy. But anyway, but let me rephrase this. This is also the smallest, and this is going to be important. This is the smallest r such that if I allow myself to embed my tensor in a larger space, that T is in the orbit closure of this so-called unit tensor. So let's unpack this. So this is just the group of changes of bases in an r-dimensional vector space. I have 3 such. So I have 3 types of basis changes I could do. That gives me an orbit. I take its closure. Eventually, if R is large enough, this thing will be in one of these. And I want to know the smallest one that it lives in there. And that is sort of agreed upon as the best measure of cost. And so now we have value. So if you ask me, that would be my answer. There's a competitor in quantum information theory where you take the asymptotic version of this. I don't have time to talk about that in the lecture, but I'd be delighted to talk about it afterwards. But the word cost and value actually does come from, can I erase these? Thanks. Yeah, I mean, I start late and then I have the board shrunk, so yeah. Please. Sorry, louder? Middle one up. Oh, then I could use this board even. Then yeah, let's not worry about that. I have enough things in life to worry about. The value is called the border subrank. Q bar of T is the largest row such that we can take, see, if we think in terms of currency, which some people do, like this thing is like a dollar or a Canadian dollar or a euro. And so this has cost and value R. And so unlike, well, like many things in life, cost is usually larger than value. So this is the value. This is the largest row such that I can degenerate my tensor and get a copy of row dollars back. So from these definitions, they look quite similar. But like I said, from the get-go, people have known that border rank is intimately connected to algebraic geometry. This other notion, up until now, up until this week perhaps, is more closely related to probability and combinatorics. So I should say that this slice rank of T is closely related to this thing. So this measure of value, this slice rank, which is also the structure, is essentially, in ways I could make precise but won't, telling us about the value of our tensor. Now, then we have this analytic rank, which measures, I remind you, failure of T to be random. And the theorem that this Cohen-Moshkevich theorem is that these two things are essentially the same. So there's constants that bound, like one is no more than twice the other, and et cetera. It's a double bound. And so now I want to go beyond finite fields to algebraic geometry and ultimately to commutative algebra. So let's see how to do this. So beyond P. So remember, this thing is defined over any field. This thing is only defined over finite fields. Right, so this will be this geometric rank. And this is one of the two tensor projects. So now let's go to that, at least for me, semi-familiar world of algebraic geometry. So given a tensor T, like I said, we could think of this as a space of matrices. And in algebraic geometry, we may want to record this as follows. So we want to do projective geometry. I want to do projective geometry at least. So we can use this anytime you have a space of matrices. You could think of this as we have a projective space. And for each point of projective space, we get a linear map from one vector space to the other. But I want to think of these not just as vector spaces, but I want to think of them as vector bundles. And this is a map between vector bundles now, where phi t over a point alpha is, well, t, I'll feed it alpha, then I'll feed it beta. So whatever this is an element of this vector space here. But here I only know alpha up to scale. So let me tensor this with some alpha star, where alpha star of alpha is 1. So alpha star, despite the name, this is an A, this is an A star. Row vector, column vector, we get a number. And maps between vector bundles, especially vector bundles on projective space, this is well studied in the algebraic geometry community. And these are almost trivial vector bundles. And so the hope is to use our algebraic geometry. Oh, there's an O of 1. Let's not go there. So let's let sigma j be the jth degeneracy locus. Let me set the dimensions all equal to m for time considerations. So co-rank, the rank drops by at least j, degeneracy locus. So this gives me a stratification of my original projective space. Right. And so we'll define the AJ geometric rank of T, GR AJ A comma J of T to be 2m minus 1 minus the dimension of this degeneracy locus minus j, and gr of t to be the minimum over j of this gr a comma j of t. So let's just work it with the case where j equals 1. So note that this thing is at most m, because if this were at most, m, because if this thing were the whole space, this would be m minus 1, and then we have these other minus 1s. Well, maybe I'm off by 1, but anyway. And right. So So for example, if j equals 1, we need P of A star to be a space of bounded rank. Wait, so let's say it this way: GR A1 less than so do I. Right. So let's look at the extreme case. Say sigma some sigma j, e.g. already sigma 1. Sigma 1 equals just the whole space. That says that no matrix has full rank. And okay, long before you set foot in this room, you know that if you take a random space of matrices, most of the matrices in that space will be of full rank. And so if I have sigma 1, or even more extreme, sigma 2, to be the entire space, that's a measure of the pathology, or the structure of my tensor. So that's, if you get nothing else out of this talk, this size of the degeneracy locus of this space of maps induced by the tensor, if it is unusually large, that is a measure of structure or pathology of my tensor. You okay with that in the middle? Okay, got some nodding heads even. Great. Right. So, so now I want to go from probability to geometry. Oh, yeah, but you want to keep seeing that. That's too bad. Okay. So this whole geometric rank was defined exactly because of the following theorem. So let's say I have tensors with integer values. And consider TP is just T where the entries I consider mod P. Then the limit as P goes to infinity of the analytic rank, now I should be precise about my field, FP of TP is exactly this geometric rank of T. And this thing is, by the way, defined over all fields. So particularly algebraically closed fields like some of us would like to be working in. And that was how they arrived at the, I don't want to erase, I don't want to erase anything. Oh, well. So that's, you look at this definition, it looks strange, especially if you know the codimension of the degeneracy loci are expected, for example, expect like sigma, like m minus square root of m to be equal to the empty set, but for geometric rank a m minus 1 of t to be less than m would imply that phi t is rank 1 on at least a curve, which you would never expect a tiny little m-dimensional subspace of m by m matrices to intersect the rank 1 matrices in a curve. That's really, really pathological. Much more than you would be indicated by the upper example, which is only a little pathological. Right. So, yeah, so like I said, T generic, say CM, tensor CM, tensor CM, then this geometric rank of T is M. And it's always less than or equal to M. And if less than, is there more chalk somewhere? If less than M, I'm sorry, I'm a chalk assassin. Windowsill. Thank you. Colors. Okay, that's okay. We'll have a colorful talk. If less than M, we'll say T has degenerate geometric rank. And so here's the first question. What are the tensors with degenerate geometric rank? And I emphasize that this is barely been, the surface has barely been scratched by algebraic geometers. We have not really started to look at this yet, which is why I think it's a very appropriate subject. Yeah, so I should also say there's another theorem the same people, namely that for geometric rank, we have the analog of row rank equals column rank. So I was surprised nobody objected that when I made this definition, I was being very biased in terms of one of my three vector spaces. And their theorem says that's okay. You're going to get the same answer no matter which space you use, not necessarily the same J. So, so this is the other question. Why? The proof is very easy. It's not a difficult proof, but there's some deep thing about a tensor that gives us three different spaces of matrices. And if one of them is pathological, the other two are also pathological, but maybe for different reasons. So I think there's something deep there waiting to be understood. So let me just point out, though. So a classical question in linear algebra is this case sigma j is the whole space. So these are spaces of matrices of bounded rank. And so just to give you an idea, so let's classify by, say, R, which will be M minus J. Classify by R. So R equals 1. This is classical. And then R less than or equal to 3. This is was done around 1983 by Atkinson and Lloyd. And then, so then we had some work by Eisenbud and Harris. We had some work by Eisenbud and Harris, didn't do anything. And then just last year, oh no, it's being taped. Can you scratch it? Yeah, so anyway, R less than or equal to 4 classified in 2023 with Amy Huang. And to give evidence that commutative algebra really has a role to play in this project, we had to use half a dozen theorems by Buxbaum and Eisenbud, not just their standard when is a complex exact theorem, but even their generalization of the Hilbert-Birch theorem to codimension 3 Gorenstein played an essential role in this classification project. So I am so delighted to be working a week with experts in commutative algebra who I'm sure should be very excited to work on these problems. Thank you.